Okay, I'll get started as people are joining in. Welcome to the weekly colloquium series of the C3.ai Digital Transformation Institute. As many of you know probably that our institute's mission is to promote the use of artificial intelligence and cloud computing to affect the digital transformation of business, government, and society. We are a consortium consisting of multiple university partners and headquartered at Berkeley and Illinois. With high performance computing support provided by the Berkeley Lab and the National Center for Supercomputing Applications. Our institute is funded by a generous donation from C3.ai and cloud computing support from Microsoft. And we also have industry partners, AstraZeneca, Baker Hughes, and Shell. Beyond today's colloquium, we have a number of colloquia in the following weeks. Alejandro Dominguez Garcia from Illinois, Roy Dong from Illinois, Deva Pracha from MIT, Ishai Manache from Microsoft Research, Murat Archak from Berkeley, John Doyle from Caltech, Sanjay Shakotai from UT Austin are some of the people who will be speaking this summer. In addition, we have an ongoing workshop. The workshop is being held every Friday for the next 2 more weeks. I guess it started last Friday. It's on machine learning for a resilient, secure, carbon-free electricity supply. And it's being organized by 3 stalwarts in this area: Duncan Callaway from Berkeley, Alejandro Dominguez Garcia from Urbana-Champaign, and Maria Illich from MIT. And we have a number of outstanding speakers, so I encourage you to attend the workshop if you're available. If you miss any of our presentations, and I guess even today some people might be signed in through YouTube, so you could either attend our events either through Zoom or via or watch it on YouTube, or you can also go back and watch it later because everything is archived in our YouTube channel. So the colloquium will be roughly 40 to 45 minutes. I said 15 minutes of Q&A, but that could be spread out through the colloquium. So if you have questions, please do put them in the Q&A, and I'll ask the speaker. If you can upload a question if you like, and if there are some questions that get more votes, then we'll give priority to them. We'll try to answer as many questions as time will allow. So today's colloquium is on the topic of security of cyber-physical systems. And the speaker is one of my academic heroes, Professor P.R. Kumar, who was a longtime professor at the University of Illinois at Urbana-Champaign in the Department of Electrical Engineering, Electrical and Computer Engineering, Coordinated Science Lab. But since 2012, he's been at Texas A&M University. His current focus current focus includes machine learning, cyber-physical systems, security, privacy, UTM, 5G, wireless networks, and power systems. He has won a number of awards. He's a member of the U.S. National Academy of Engineering, the World Academy of Sciences, and the Indian National Academy of Engineering. His honors include an honorary doctorate from ETH, the IEEE Field Award for Control Systems, the Ekman Award from the American Association of American Automatic Control Council, the Ellersick Prize of the IEEE Communication Society, the Outstanding Contribution Award of ACM Sigmobile, the Infocom Achievement Award, and the Sigmobile Test of Time Paper Award. He's a fellow of both the IEEE and ACM. Kumar has made outstanding contributions to so many areas. It's very difficult to pin down a particular field for him, and that sort of is reflected in his research interests as well as his awards. So today he'll be talking about security for cyber-physical systems, and without further ado, I'll leave the floor to Kumar.
Thank you, Srikanth. It's a pleasure to be here and talk to you folks. So I'm going to share my slides. And okay, so here are the people who do all the work. The thesis of watermarking was started with Bharadwaj Satchidanandan, who's currently a postdoc at MIT, and then a whole lot of other people here. Okay, cyber-physical systems, I don't need to tell you what they are. They're computing, communication, control are tightly integrated, and many societally important applications, and they're safety critical and economy critical. And they are vulnerable to attacks because changing bits in the cyber domain can cause physical damage. And indeed, there have been a number of such attacks. Okay, so let's first start with how to abstract this problem of defending cyber-physical systems. The overall system has a physical plant at its core, which could be a power system or an automobile. And there are actuators, which could be the gas pedal or a generator or something. And there are sensors, which could be a speedometer or a PMU measuring frequency or voltage. And the loop is closed through a network, which may consist of just router nodes or information processing nodes or whatever, okay? The issue is that some of these nodes may be compromised. Some actuators, routers, sensors, etc. may be compromised. And the question is, how do we secure the overall cyber-physical system? So we're going to abstract the security problem. And we'll say that if information from a sensor is compromised, we say the sensor is compromised. In other words, we really don't care where the sensor information is compromised. As long as information is compromised, the sensor is compromised. So we can simplify the abstraction to, we have a bunch of actuators and sensors, and some actuators and sensors are compromised. That's all. And just get rid of the network and the information processing nodes. And the problem is, how do we secure this overall cyber-physical system? And today I'm going to focus mostly on compromised sensors, not so much on the actuator case. Okay, first we're going to have some fun. Okay, let's do some theory. Let's revisit the era of Kalman, which examined linear systems in more innocent times. And here's your linear system. And the question is it controllable? And the issue of controllability is addressed, and then also the issue of stabilizability. And similarly for observability and detectability. Okay. Now, but let's try to look at a more paranoid version of a theory of linear systems. So some of the inputs may be compromised, and some of the measurements wise may be compromised. So what harm can malicious sensors actuators cause without the honest sensors actuators knowledge? Okay, so we have this paranoid linear system. It could be linear deterministic or stochastic system, and if you want to generalize a little bit, that can come from a small signal model of physical plant. And the malicious actuators and sensors can collude, and the honest actuator sensors don't know which nodes are malicious. Okay, can the honest nodes diagnose the system, and what performance can they achieve? So the new age concerns versus the innocent age concerns are, in the old days, the random noise was kind of benign. Now we have malicious agents that cause harm. Earlier, we were concerned with things like stabilizability, detectability. And here I'm going to coin a new phrase called securability of malicious systems. And the good performance of linear systems, we want to study the security of malicious systems. Okay, so continuing in this fun theme, let's look at security guarantees based on system structure, just like Kalman would have done, I suppose. So let's look at deterministic system. And I want to define something called the securable and unsecurable subspaces for deterministic systems. So supposing we have a linear system, and I'm throwing away the honest sensors, we can assume they're 0. So we have a bunch of malicious actuators which are inputting UM, and we get observations Y, and these are the honest sensors. And what states can the malicious sensors or actuators drive the system to without the honest sensors or actuators ever finding out? Okay. And the unsecurable subspace is the set of states that the malicious sensors and actuators can keep indistinguishable from 0 state. And its orthogonal complement is the securable subspace. So here is a characterization of this unsecurable states. So the X0, an initial condition, can be made indistinguishable from 0 if there is a sequence of inputs such that the honest sensors see 0 on the first day, and on the second day, you can apply some inputs to again make you see 0, and so on. Okay, and basically the unsecurable subspace is then the maximal subspace V, such that for every vector in the subspace, it's in the null space of CH, and there exists an input U such that it preserves it on the next transition within V. And the securable subspace is the orthogonal complement. Now let's take a look at the Kalman filter, okay, just to see what would happen in that context. So suppose I have a noisily observed linear stochastic system, all standard white Gaussian noises, and the true outputs are Y, and this is a notation that you'll have to keep track of throughout. True outputs are Y, but the sensors report Z, okay? So the honest sensors will report honest measurements, and the malicious sensors will report malicious measurements. Okay, so we can assume that the first group of measurements, first set of components of Y are honest, and the remaining components are malicious. And the malicious actuators may apply an input D of T, which may differ from 0. Okay, all right. Now, if everything was innocent, and if the outputs could be accurately measured and the inputs were known, then the correct Kalman filter would be like this, which uses an innovations process nu-C, and so it employs the correct innovations and it under standard conditions. Okay, but the incorrect Kalman filter, which would be implemented in a malicious setting, would use Z rather than V in the innovations, and it would assume that the malicious inputs are 0. So the incorrect Kalman filter indexed by I would use these things where it's feeding off of incorrect measurements. Okay, and now what we can do is we can, without taking any active measures, we can just perform an additional check on the presumed innovations, and we can check whether the innovations process is right. Okay, and here's a guarantee, here's a theorem. If the innovations test passes, then you can guarantee that the estimate of the state in the securable subspace is actually, the error is actually 0. Okay, so that part of the state you can get right. And so the incorrect estimate of the state is as good as the correct estimate of the state on the securable subspace. Okay, so that fun is over. Now let's move on to more practical concerns. So in this era of paranoia, what can we do vis-a-vis security through active means? Everything else was passive. I was just re-examining linear systems. And the basic idea that I'm going to use is what is called dynamic watermarking. So here we have a physical plant, and these are the sensor measurements. And let Y of T be the actual measurements of the sensors, but some of these sensors may be compromised, and they actually report a vector Z, not all of whose components are accurate. Okay. Now the loop is closed by the actuators who actually use the incorrect measurement Z to choose their control inputs. Okay. Now, the basic technique that we're going to use is we're going to superimpose a private excitation on the input. So I'm going to add, you can think of it as a white noise. I simply add a white noise to the input. Now I can announce to everybody that I'm adding white noise, and I can tell you the statistics, mean, variance, all that stuff, just like a asymmetric key cryptography. But I won't tell you the actual waveform. Okay. So I'll keep the actual stochastic process as private, but I can disclose its statistics. Now, why does this help? Okay, so the net input is the superposition of what it applies based on the incorrect measurements plus this private watermark. Okay, why do we call it a watermark? This random noise will percolate through the physical system and cannot be removed, just like a watermark in a piece of paper, right? You cannot remove the watermark from the paper. So it will percolate through the system and eventually show up at the sensor nodes in some transformed way. And those measurements are returned to you. Now you can examine those measurements and kind of correlate them or examine them in the context of the watermark that you applied, and you can build an attack detector. And this attack detector then will tell you if there is an attack going on or not. Okay. Let me take a simple first order single input, single output system. And if you understand that, you get the basic idea. So here is a simple system. XT plus 1 is AXT plus BUT plus white Gaussian noise. And the main things I want you to focus on is that the variance of this state noise process is sigma squared W. Okay, keep that in mind. Now, what watermarking does is, to the input that it applies based on the return sensor measurements, it adds a watermark ET. And the main thing I want you to keep in mind is that this watermark ET has variance sigma squared E. Okay, it's also white Gaussian. Okay, now the closed loop system, after you plug in this value of U, will have AXT plus BUGT plus BET plus W. Now we can take the same equation and rewrite it in two different ways. In one way, I'm only going to preserve W on the right-hand side, move everything else over to the left-hand side. And the other way is I'll preserve BE plus W on the right-hand side and everything else over to the left-hand side. So here is just the state noise And here is the watermark plus the state noise. Now, this state noise should have a variance sigma squared W, and this watermark plus state noise should have a variance, because they're independent, sigma squared W plus sigma squared V squared sigma squared E. And all we're simply going to do is test for those variances. We'll take the left-hand sides of these things and check whether their empirical variance is sigma squared W or B squared sigma squared E plus sigma squared W. And can this test be conducted? For sure, because it's using the presumed values of the state, and it knows its own watermark. Okay. So these are two tests, test one and test two. Now, our theory is completely restricted to just detecting whether there's an attack going on. So if either test fails, then clearly there is an attack going on. And what do you do then? So I don't say anything about that. That depends on the context. The system could go into a safety mode, it could be halted, it could be rebooted, it could go to manual operation, etc. For example, if you're driving a car on a lonely highway, you could just stop it. But if you're in a quadrotor, maybe you need to land. If you're in a slow time scale chemical process, you go from automatic to manual operation and so on. But I don't address what the recourse should be. Now, the issue is this: passing these tests is clearly necessary for the system not to have something wrong with it. But is it sufficient? That's the big question. And here's the theorem. The fundamental theorem is the following. Define this signal V. I'll explain to you what V is in a second. And the fundamental guarantee of the watermarking theorem is that the empirical variance of V is 0. Okay. Now, what's the interpretation of this? What is V? If you reorganize the system, you can write the system as mimicking the state space description of the true system, which is xt plus 1 minus axt minus bugt minus be, would normally equal W. But now it has the V. So what we're saying is the only damage that the malicious sensor can cause is to effectively add a 0 power signal V to the already present ambient white noise in this noise process in the system. So they can, the only damage is they can add a 0 power signal to the noise. Now 0 power doesn't mean 0, okay, but it's a 0 power. Okay, now the proof of this is actually quite subtle, but I'm not going to go through that. Now, from that fundamental guarantee of watermarking, fundamental theorem, you can give several guarantees. For example, if the system is open loop stable, then you can show that the distortion introduced between Z, the measurement, and the actual is 0 power. The mean square performance of the system is what you presume it is. And you can also talk of stability and all kinds of things. Okay? All right. Now, these results, though I illustrated for a single input, single output system, they extend to general RMAC processes, which are very, very popular in process control, or MIMO, partially observed Gaussian systems, which are the models for electromechanical mechanical systems. Okay. Let me take an example, just to give you a little bit of a flavor. So take a model RMAX process that you'd find in a process control system. So Y's are the outputs, and this is the noise, and this is the inputs. And let us suppose it's a minimum variance control. For example, very popular in process control, paper mills, and so on. You apply a certain input to make the variance of Y as small as possible. And I also add a watermark here. This is the closed loop system. Now, the attacker doesn't know what watermark you applied, but it could estimate the process noise through this formula, and then it can actually create a fake system with simulate a fake system with a noise NT by actually injecting N minus this W hat. So this is like the Stuxnet attack, which took a fictitious simulation output and gave it to the controller. It's like that. Okay. Now, in the absence of watermarking, the actuator would not suspect any malicious measurements. This attack is much more sophisticated than the Stuxnet attack, okay? Because you're estimating process noise and so on. Now, in this case, let us say the sensor attack begins at time 4500. And here is one of the tests, test 1 or test 2, I don't know which one. But immediately, the test flags that there has been an attack on the system. Okay? So this is the kind of test indicators that we are watching out for. Now, let me cover a little bit more of the theory, then we'll go to some implementations. Do we really need both tests? And the answer is yes. This is a counterexample of a system which can pass test 1, which passes test 1. Okay, so you need test 2. And here's a counterexample of a system which passes test 2, showing that you do need another test. You can also ask, what about non-Gaussian noise? It turns out that we can address non-Gaussian noise, but we cannot make the watermark negligible. And then there's also characterization of when the watermark guarantee is feasible for what kind of noise distributions and so on. So there's a characterization. Okay, let me turn now to implementations. Okay, so this is so first we started off by implementing this in a laboratory version of an autonomous transportation system. And here is a photograph of our lab. Okay, it has a complete closed loop environment. And here is a film made by our engineering publicity person, which I thought was pretty good actually. So this is a sophisticated system which has collision avoidance. So even if a human being is trying to cause collisions, it stops. But if you attack the sensors, you can still have collisions. So there is a collision, okay? Now we'll switch on dynamic watermarking to see if it can forestall the collision. Okay, unfortunately, there's nothing interesting to see because the watermark catches that something is wrong and just halts the vehicles in this case. Okay, all right. And if you want to look at the equations, this is the watermark system, and this figure is actually important. A lot of times, the people, yeah, go ahead.
So by adding this watermark, does it affect the performance of the system in some manner? I mean, in this example, it didn't say.
Right, it's a perfect question, and this is the exact graph. So this is the performance of the system with and without watermarking, and watermark doesn't result in any added penalty. And I'll be showing you similar graphs later also, okay? So this thing is imperceptible to a user, but can be recognized by delicate signal processing, basically, okay? That's
but when you add the noise to the
correct
system, you're changing the controller slightly, right? So if the controller is expected to have some desired performance,
so minute that it's imperceptible, but it can be detected by fine signal processing.
I see.
Protect the system. Okay.
Okay.
And this was a bias attack, and this particular attack fails test 1. So test 1 catches it and it crosses some 3 sigma threshold, and test 2, however, passes it. Okay. Now the question is, does it actually work in a road vehicle where the tire meets the road? Okay, and I don't mean that. I don't mean that metaphorically. So this is a very important question because simulation models, any simulation model, whether you take a mechanical system or an automobile or a process control system or a power system, they only capture the Newtonian or Kirchhoff dynamics. Okay, there is never a model of the noise. Okay, and vehicle simulation models only model the deterministic part. However, our theory of defense relies fundamentally on stochastic considerations. It relies on the inability of an attacker to separate system noise from watermark. Okay, so we need what is road noise in this case? I don't think there's a model of road noise. Okay, so the test of the pudding is only in the tasting, and we did an actual implementation on Lincoln MKZ in our Relis campus, and yeah, so this is a system that you can actually go into, and it's completely open. And this is I'm showing you an example of a yaw rate sensor attack. Unfortunately, not much to see because after some time this vehicle will just stop. Okay, that's all it is. Okay, so it actually works. So it's not an exciting video because when you have security, it's not exciting. Okay, and the watermarks again in this case also, but we tested very, very small watermarks, okay, addressing Srikant's question. So magnitude effectively doesn't matter. Okay, now our claim is that we want something that's the general purpose defense. Okay, so here's a process control system, which is a bedrock of industry. So we took a laboratory 2-tank system. So this is a 2 tanks and water flows into the top tank, and then from there it flows into the bottom tank. And you want to control the levels of these 2 tanks, Y1 and Y2. And the way you control the level is by controlling the voltage of this electric motor. So the input is U, the voltage, the outputs are 2 levels, and these levels are measured through a pressure sensor at the bottom, okay? And they could be compromised, okay? And attack could be, you may want to cause overflow. You may want to cause overflow of the tanks or something. So here is so now this is just initialization, okay? The system is just filling up. After some transients, it will reach a steady state. I think we're near the steady state. Okay, now the system is doing fine. Well, not yet. So now the system is doing fine. The 2 tank levels are regulated, but now the attack starts. So the level is misreported, and there are many, many ways of misreporting the level. And what happens is, in the absence of watermarking, when the attack starts, it just overflows. Okay, the tank overflows. Now, so okay. Now, in this particular case, oh, sorry, apologies. I should tell you. Now, what does watermarking do? So watermarking catches that, okay? Oops, sorry. My apologies. I think I prematurely stopped it. Now, the watermarking then will catch it and will drain the tank. The recourse in that case is to drain it. I give up. My video is not playing. But what I want to show you is this froth, okay? This is the noise in the system, and there is no model of froth. And this watermark would penetrate through this froth and be detectable, okay? And so watermark has to survive this noise, and dynamic watermarking is fundamentally a stochastic approach, and there are no simulation models. So simulation is not enough. You have to do experimentation. Okay, the next is not an actual demonstration, but it's a simulation because they won't let us get anywhere near big power system. So this is automatic generation control. So let us say you have many areas. Say there are n areas, and each area you want generation and consumption to be about equal, generation and demand to be about equal. But occasionally, if there is a high temperature in Houston, a neighboring area may help it by shipping it power. Okay, so that is automatic generation controls. So the way it works is that that's area 1. There's a group of generators. That's area 2, area n-1, area n. And each of these generators is producing some output power and frequency. Okay, frequency is omega. And the power is shared among these areas through some tie lines, and you can also monitor the frequencies and so on. And here is a multivariable feedback, which then, depending on which area is deficit of power and which is excess, it resets the set points. Okay, so the controller is resetting the set points for the generator. So for example, if one area is in deficit, it asks its generators to produce more. Now, what is our defense here? We inject a private injection to each of these noise into each of these generators. So AGC monitors frequency deviations and tie line flows across multiple areas and closes the loop. It controls both frequency deviations and tie line power flows so that each area properly responds to its own load changes. And it operates in the 30 seconds to 20 minutes time scale. Now, here's a way to attack the power grid. If these frequencies nowadays are measured by phasor measurement units or synchro phasors, and if you underreport the frequency, the operator may think that, hey, listen, there is more demand than supply, okay, because the frequency is dropping, and may do load shedding or something. Or conversely, if you think that if you overreport the frequency, then he may shut down generation and so on. So very simple to attack it, and the defense is through watermarking. And this is a simulation of a 4-area synthetic power system with 10 generators. And again, this is the performance of the system with and without watermarking, and the imperceptible difference. And so here is the attack starts in this case at 10 minutes, and the operator would only recognize it at 18 minutes when it crosses some 3 sigma limit or something. Okay, but watermarking will detect it instantly. Okay, so we can catch such an attack instantly, and in fact we can even catch attacks which kind of flirt with the 3 sigma level but don't actually cross it. Okay, all right. The next is, this is an actual project. This is a large
a couple of questions in the Q&A, since you said you'll take questions in the middle.
Yeah, absolutely.
So one of them says that if one does not have access to the actuator signal, can the watermark be added to a reference input such as a water level setting? Is there a different way to add the watermark if you don't have access to the actuator signal?
Yeah, so I mean, if you think of the reference signal as an outer loop, so there's an inner loop and then there's an outer loop, a slow timescale outer loop, then you're doing watermarking on a slow timescale outer loop. In fact, that's what we're doing here. We're setting the reference power levels for the generators, right? So that's what's going on here.
Yeah, so the question was from Prasad Enjeti. The next question is from Romil Sonigra, who says, I guess he's just wants you to emphasize what you said earlier, I guess. The statistical properties can be known to others. However, the exact values of the private signal is the only one that's unknown, right?
Yes. Yeah. So the stochastic process sample path I'm going to keep secret. Or for example, the seed of a random number generator I may keep secret. But I can announce to you the variance and stuff. So here is,
I guess, can people infer the statistics in some manner? I guess is that why you're saying that it doesn't matter even if they know statistics, or?
Statistics don't matter because
exactly
the theorem, there's a theorem. So,
correct. The statistics, okay. So it's only so what I'm saying is then, does it even have to, I mean, my question is the statistical, I mean, does it even have to be statistical? I guess that's my point. I mean, in the sense
it could be pseudo-random.
Right, or just I guess if we just add a deterministic signal, I guess it's impossible to figure out. You can't express everything in terms of variance and so on. So basically, think of it statistically, but then saying that, right? It's just the way.
Yeah. Okay. Unless I mean, if it's a deterministic signal composed of 2 or 3 harmonics, then I can actually estimate. By the way, no, it's not going to quite work that way, because if you have a white noise with a smooth spectrum, and then you have a certain frequency delta function in the spectrum, I can recognize it right away, FFT. Okay. So you have to be careful.
Okay, thank you.
All right, so now is an attack on a solar powered distribution system. So we're talking of the future where, I mean, there's increasing use of solar power generation. Many homes in the future will have solar rooftop panels. And this is an example of what are called distributed energy resources. And we may, down the road, have a photovoltaic dominated distribution grid. Okay, so the picture is something like this. You have a bunch of homes with solar panels and with power electronic inverters and so on. And they're all interfaced to the grid. Okay, so they can supply power to the grid or take power from it when the sun is not shining and so on. And now, you have a large number of these. So somebody has hijacked the signals that are going into the controllers for the inverters, they could bring down the whole distribution system. Okay, so you can have an attack on a large number of edge devices. So we have a preliminary implementation of a laboratory scale grid tied inverter. So on the left half of the top picture, you see this is the photovoltaic source, and you have the inverters here, and they're connected, interfaced with the grid. So you have these interface variables, the current, grid current, and the grid voltage. And then you have a controller here for the inverter. And if somebody hijacks some of these measurements, then they can cause damage. And what we do is we inject a watermark over here and use that for an attack detection algorithm. And these are preliminary results that we have. Okay. And this is a large DOE project with industry, Argonne National Lab collaboration, which aims at implementation. All right. Now here's an attack on an aerial vehicle flight control system. So this is a laboratory model of a helicopter. And again, you can subject this to an attack, right? And in this particular case, the attack that we're doing is we're injecting a kind of a random noise or bias into the elevation measurements. And the watermarking tests again, test work, and it detects with a delay less than 100 milliseconds, it detects it. Okay, so let me just make some concluding remarks, and I think I'm exactly within your 40-minute guideline. So this could be a possible general purpose defense of cyber-physical system. And these cyber-physical systems have a lot of societally and economically important future infrastructure will be cyber-physical system and will therefore be vulnerable. And without security guarantees, there's going to be resistance to the proliferation of this technology. People want guarantees. As you start networking more, as you start opening up more, as you start giving systems more intelligence and autonomy and so on, they also become more vulnerable to attacks. So it's absolutely important to understand how to, at least in this case, detect the presence of an attack. And this is a possible general purpose defense that we are proposing. And there are many problems. And there's a whole bunch of references. And I will stop there. Thank you very much. I think I'm right on time.
Thank you very much, Kumar. Thank you for that fascinating talk. I mean, normally people think of security as a very computer systems oriented discipline. I think this is, looking at it from a system theoretic perspective is really refreshing and very interesting. Thank you for the fascinating talk. So if there are any questions, please put them in the Q&A. I guess I see one, and the panelists too, if there are any questions, please feel free to ask. So the one question we have from Tong Huang is, can we extend the watermark idea to nonlinear systems?
Yeah, that's a very interesting question. So we are actually looking at that. Some approaches are, one is feedback linearization. Now clearly you can get necessary conditions quite easily. Sufficient conditions are the challenge. Yeah. I wanted to add one thing in response to your comments, Srikanth, and that is, so this is a system theoretic defense, but it can detect attacks happening in the packet network domain.
Okay.
Because even if you fool around completely in the cyber layer, at the bit layer, at the packet level, whatever, router level, this will detect it because it's basically checking information.
So are you saying that if people inject spurious packets or something like that, is that what you're saying?
Yeah, sure, we can catch that. Yeah, anything.
Okay, I see.
Yeah, so we don't have to, so it also tests the network. If you.
Okay.
And the other comment I also want to make is that it's not just malicious activity that it can detect. It can also detect failed sensors. So this is another issue, actually very important issue. When you have a distributed system with sensors all over the place, for example, PMUs and so on, and how do you know that some of them have not failed? You can't go and check each one of them. And actually the whole issue of sensor calibration is a very important area. When you have sensor networks, how do you calibrate these sensors? If it's a large distributed system with a lot of cheap sensors, You cannot go to a riverbed where you immerse a lot of sensors and check them again, So you can do that. And if you think about it, there is very little difference between sensor failure and malicious attack on a sensor, because it only lies in the intention, right? And the intention is in your heart, and I have no clue what that is. So yeah, so it's impervious to both.
So I guess there is a question from your former master student, Ravikant. Actually, he posted a question, I guess. Yeah, I know that this talk is a talk about cyber physical systems, but are there ways to apply the concept of watermarking to detect attacks on information systems and such? I guess that's partly what you answered earlier, maybe? You said.
Yeah. Yeah. Go ahead, Ravikant.
I guess he can't ask because I have to ask the question. Yeah. I just read it. Yeah. So is there other ways to apply the concept of watermarking to detect attacks on information systems? Yeah.
Yeah. So that's something I'm thinking about. See, for example, what is it called? It's called traffic analysis, right?
All right.
So through traffic analysis, you can actually deduce something and so on. So attackers can get information and so on. So one possibility is to kind of inject noise into packet timings and things like that. So yeah, so we're looking at those kinds of possibilities also. Yeah.
So this thing about you mentioned about sensors failing. So one of the use cases that people at C3AI, the company, not our institute, the ones who sponsor, the people who are sponsoring our institute, one of the use cases for their software they mention is what is called preventive maintenance or predictive maintenance. Mm-hmm. So the idea is that the major companies have like oil rigs and so on face huge amounts of downtime because mm-hmm. sensors fail. And because sensors fail, they can't continue operation because something goes wrong. So they want to predict when sensors are going to fail, and then they not sensors. Actually, they have sensors which detect if some components of the system are going to fail, and based on that, they can predictively, they proactively do maintenance. So what you are saying is that if the sensor itself fails, then you need to know that. And so in a large distributed system, how can you? Is it possible to use your theory to figure out which sensor failed? I mean, because there could be thousands of sensors or tens of thousands of sensors. Sometimes.
So I've not addressed that issue here. Okay, but that can be done in the following way. We are checking every individual measurement, right? We can check every individual measurement from a sensor. Mm-hmm. So that way I can tell you which measurement is wrong. Okay, so that's possible. That's one thing. The second thing I want to say is actually very, very interesting. I forget the next generation of manufacturing. There's a buzzword for it. Anyway, so it turns out this very good question. People have said, hey, listen, if you can put more sensors and detect tool wear and failure and so on, then people can actually do preventive replacement and so on. So the story I've heard is companies that have tried it, it turns out the mechanics currently are not trained enough to recognize what to do if a sensor is working but not perfectly. They simply are not trained. Okay. So something is broken, then they just come and replace it. But what do you do? And it turns out that companies that have actually done this, they haven't gotten any benefit because they don't know what to do. But one thing that you could do is you could generally trace or use this watermarking a technique to trace the degradation of the tests, right? And maybe calibrate that with some level at which you declare it has failed and so on. So it's possible. But there is this real world challenge of if you give a mechanic this information, this variance is 2.8, the person has no clue what to do with that information. Yeah. So, so there are some additional challenges. Yes.
Okay. So for the audience, if there are any questions, please post them on chat. So maybe we'll wait for a minute or so, and if there are no more questions, we can wrap it up. Okay, thank you, Kumar, for the wonderful talk.
Pleasure.
I mean, this is a really interesting way of looking at security. It's really eye-opening for me. Thank you once again, and
thank you.
I'll applaud. And yeah, thank you. Bye.
Thank you. Pleasure. Okay, bye-bye.